In this video, we're going to discuss how to interpret the F ratio, a little bit about hypothesis testing, and then also how do we measure effect size with the analysis of variance. So if the null hypothesis is true, the F value will be around 1. So let's think about that F ratio. Mean squared between, so our variance between subjects over our mean squared within, our variance within subjects. And we said that this numerator is any effect that we have from the treatment plus any error from other components like just random chance, individual differences, and the denominator is just that what we would expect based on chance and error. So that's the variance in the denominator. Now, if these numbers are similar, meaning that there's not very much of a treatment effect, because adding a treatment effect would make the numerator much bigger, we're going to get a value close to 1. As we go out here and we get values that are much bigger than 1, that's when we would properly reject the null hypothesis. And because the F ratios are computed from two variances, they're always going to be positive numbers. So the F values are organized by 2 degrees of freedom. So yes, we did calculate 3. We had a degrees of freedom total as well, and we'll see that on the next slide. But the ones that are important in knowing how to interpret that F ratio and determine if we're going to reject the null hypothesis is the degrees of freedom in the numerator, which is our degrees of freedom between subjects, which was our k minus 1, and degrees of freedom in the denominator, which is our big N minus k. So again, here's the degrees of freedom in our numerator. Here's our degrees of freedom in our denominator. So when we're looking at the table, and this table is a little different than the one that's in your textbook. The one in your textbook has both 0.05 and 0.01 significant values together, and they have light face and bold face. I couldn't get that into the lecture notes, so I went with one that I found that has 2 separate tables that I have downloaded and put up into the module for you. So when we're looking here, the columns, so these are the columns here, right? 1, 2, 1, 2, 3, 4, 5. Those are the columns. These columns represent our numerator. So this is the degrees of freedom in the numerator, which is also k minus 1. The rows is degrees of freedom in the denominator, or n minus k. So for our study, we have degrees of freedom 2 and 12. That gives us a critical value of 3.89. And I see the value I have here is 3.88, and I will try to find a new table, or I will upload the table from the textbook. I'll have to scan it in to fix that, but just so I can get this video up for you, I'm going to go with that. So it's different in this table. Here it does say 3.89, but if you go to degrees of freedom 2 in the numerator and 12 in the denominator in our textbook, it says 3.88. So that's why this value is that here. So this is what a table would look like, very similar in SPSS output, minus how the F ratio is reported. But just you will have to get familiar with this table throughout the next couple of weeks. Part of the practice problems that you'll be doing, both for me in class and then also for the MindTap exercises, will have tables like this and might have a few numbers in there, and then you have to fill in the gaps using information that you know and what's in the table and so on and so forth. So here, just filling in for between treatments, this was the sum of squared deviations for between treatments that we calculated. This is the degrees of freedom here. Within treatments, this was that sum of squared deviations that we calculated. This is degrees of freedom for within subjects, within treatments. Here was our total sum of squared deviations, and here was our total degrees of freedom. We calculated that MS, which was SS over, so 30 divided by 2. The within treatments MS was 16 divided by 12. We then take 15 and divide that by 1.33, and we get our 11.27. And so this is how you would report it, with degrees of freedom between and degrees of freedom within. So hypothesis testing with ANOVA, similar to the other hypothesis tests we've done. First, you're going to state the null hypothesis and alternative hypothesis, which we've done in previous videos. We just showed how to locate the critical region using the F distribution table and degrees of freedom. We then calculate the F ratio, which is done in stages. First, you have to calculate your sum of squared deviations, then you have to get your MS values, and then you compute your F. Then you compare this calculated F to your critical F, and you make a decision. So for that one, if we said that our critical F was 3.88 and our calculated F is 11.27, we would definitely reject the null hypothesis. So now to measure effect size. So you can compute the percentage of variance that's accounted for by the treatment conditions. And for ANOVAs, we typically use what's called eta squared. Or sometimes they do what's called partial eta squared, where you have a little p. It's a slightly different formula. So we're going to learn how to calculate eta squared. So for that, we just take our sum of squared deviations for between treatments, which was 30. We put that over the total, and that's going to give us a value of. And again, most publications require the reporting now of these effect sizes in addition to simple significance testing, because they want to know, regardless of the sample size, how big is that effect that was seen in the study, in the experiment. So in the literature, means and standard deviations are presented in the text. The results of ANOVA are going to be summarized, including your F and your degrees of freedom, your P and your eta squared, in this format. So you would have a sentence describing that the results of the analysis of variance showed a significant difference, and then you'd write, here's you're telling you what statistic you're doing, your degrees of freedom between, your degrees of freedom within, this is your calculated F value, this is the P value, the alpha level, that you chose, and this is your partial eta squared. This is your effect size. When we're doing an ANOVA, we're also making some assumptions. Again, for this independent measures ANOVA, we're making the assumptions that the observation in each sample must be independent. The population from which samples are selected must be normal. The populations from which the samples are selected must have equal variances, and this is our idea of homogeneity of variance. And so when you do an analysis of variance in SPSS, it will pop up and tell you if your populations had equal variances. It wants to make sure that those the samples have equal variances, and if it doesn't, then you violated the assumptions and your calculations are not accurate.